Hello, welcome back. Let's continue where we left off. We created a structure representing all the registers we need in order to configure our GPIO ports. We need to create a structure to represent all the registers we need to configure our buses. Our buses, remember we have the AHB bus, APB bus, and we have AHB1 to APB1 to. They are also arranged in a particular pattern, and we need to create a similar structure in order to be able to work with them. So I'll go back to the reference manual over here, and I'll go back to the table of content and see the bit that talks about RCC. Okay, so this is the bit that talks about RCC. And we have so many registers over here. I think we have over 31 registers. This one starts with the RCC clock register, and then after that we have the PLL configuration register, and then we have another configuration register, and then we have these. So we've got to create the same arrangement. So I'm going to click on RCC registers, right, and I'm going to come over here to our CalU Vision, and I'm going to create a new structure. I'll say type def struct I'll call this RCC type def. Like this. I wrote GPIO, sorry. So I'll call this RCC type def. Okay, so the first register is the RCC CR register. It's called offset 0x00. So I'm gonna say, like I did before, __ IO uint32 _ C. The register is called CR, and this CR stands for clock control register, right? So the next register after that, let's see, I'll scroll down. The next register is the PLL configuration register. PLL stands for phase locked loop. We use this to change the frequency of our microcontroller. So I say IO uint32 _ T PLL CFGR. The one after that, let's see. Okay, this is the offset, meaning the third element, and the register is CFGR. So I'll do _ IO uint32 CFGR. Following that is the CIR register. This is the clock interrupt register. This is the offset, so it would correspond with this position, _ IO uint32 _ T, and the register is CIR, like this. The one after that, let's see, is the AHB1 reset register. Okay, so _ IO uint32 _ T AHB1 R STR, like this. AHB1 reset register. Right, let's see the next one. The next one is AHB2 reset register. So I'm simply going to copy this, then paste it over here, and then this one becomes 2. Okay, let's see the next one. The next one is the APB. I think there should be APB1 before APB2. Okay, so there's the APB1 reset register. So I'm simply going to paste this and change this to APB1, and then the one after that is APB2 reset register. I'm going to paste this, change this to APB2, and the one after that is I think we missed one. Let's go back to the top, sorry about that. So we started with, let's go back to AHB. Okay, we started with AHB1 reset register, and then AHB2 reset register. Yeah, the problem I sense over here is, you see, when we take AHB2 reset register, the next one is APB1 reset register, but the offset from here to here is not simply +4, it is more than that, you see. So if we simply put it in our, if we arrange it in our structure by simply putting this register under this, the address of this is going to end up being 0x18. So that has to change. We need to we need to pad it, we need to put some space between it. So I'm going to just put some dummy variables, dummy members between this and this, so that the position of this would correspond to 0x20. I hope you understand what I'm talking about. So between this register and this register, I must pad the middle with 2 uint 32-bit data types. If you see this is 0x14. After this, if I add 4 bytes to this, this will become 0x1c. If I add another 4 bytes, then this will bring me to 0x20. So I'm going to have dummy 1 and 2 between this, right? So over here, after AHB2, like we said, it's going to be between AHB2 reset register and APB1 reset register. AHB2 reset. Okay, so I'll come over here. I don't need to do it volatile. I can simply say uint 32_t. I'll call this dummy 1. And then I'll have another dummy here, uint 32_t, dummy 2. Right. So when we get here, then we are at 0x20. Right. Okay, so let's see. We have to keep an eye out for things like this. So after this, we had APB2 reset register. If you don't understand what I just did, kindly send me a message. So we have AHB2 reset register. Let's see, APB2 reset. Okay, that is just 4 bytes. 0x20 plus 0x04 gives us 0x24. Right. So after this, after APB2 reset register, let's see what we have. So this is our current offset position, and it corresponds to the position here in our structure. So the next register over here, let's see, is the AHP1 enable register, right? And that is way off. That is 8 bytes away from our last stopping position. You see, this is 0x30 and we stopped at 0x24. So we need to put something between. We need to put 4 and then 4. We need to put two 32-bit or two 4-byte data types, which is 8 byte, in order to arrive at this position. This is where we left off. This is where we are currently, 0x24, and the next address should fall on 0x30. So what I'm gonna do is I'm gonna create dummy 3, and this time, rather than make it an array, rather than do it twice, I can even use an array. So I'll just say uint32_t, and then I'll call this dummy 3, and this an array of size 2, right? So then the next element would fall on 0x30, which is this over here, AHP1 enable register. And this AHP1 enable register, this is where we need to access in order to enable our GPIO. So I'll say __IO uint32_t, and the name of the register is AHP1 enable AHP1 ENR, like this, right? AHP1 enable. Okay, so it's a 0x30. So the next register we should expect 0x34. Otherwise we would need to add a bit of dummy. Okay, indeed, 0x34, this AHP2 enable register. So we don't need to pad it. We can simply paste this here, this AHP2. The one after that is the APB. Sorry about that. This is the APB1 enable register, and this is, let's see, where this the last address we left off is this, and then we've got this APB1. Definitely we need to pad. We need to pad with 2 uint32-bit items. So I'll come over here and add dummy 4, dummy 5, uint32_t, dummy 4, uint32_t, dummy 5. Right, so let's see what is next. Yeah, we did this padding in order to arrive at APB1 enable register. So I'm gonna do that. Come down here, __IO uint32_t. The name of the register is APB1 enable register. It's the same as this, but this is AHP1, right? APB1 ENR. Okay, so let's see who's the next register in the line. So we APB1, we at 0x40. The next one should be 0x44. Otherwise we would have to pad. Okay, 0x44 APB2 enable register, no padding required. I'll copy this, paste it over here, change 1 to 2 over here like this. Right, the one after this, let's see who is next. I'm gonna scroll down. The one after this is the peripheral clock enable low power mode AHP1 LP enable. Yeah, we need to pad 0x50. We need 2 dummies, or we can use the array. So I'm gonna call dummy 6 down here. You in 32_T dummy 6. I'll just, rather than do 6 and 7, I'll just use an array here like this. Okay, so the one after that, once we've padded, we can, call our guy, this register here. Okay, and start with volatile __ IO. You in 32_T. That's the name of the register. The one after that, let's take a look at it. So the next one should be 0x54. Otherwise, we would have to pad with some dummies. Okay, no padding required. It's simply AHP2 low power enable. Right, like this. Okay, let's see who is next. So the next one has to be 0x58. Otherwise, we would have to pad. The next one is APB1 low power enable. Okay, we need to pad. Yeah, we need to pad because we need to pad with 2. The offset is 0x60, so I'll have to call dummy 7. I'll copy the dummy from here, and I'm gonna use the array method. I'll call this dummy 7. Right. Okay, so once we've padded, now we are at 0x60, and the name of the register is APB1 low power. So I'm simply gonna copy this because we've already typed this before. Paste this over here and change AH to AP like this. Okay, and the one after that, let's take a look at it. The one after that has to be 0x64, otherwise padding will be required. Let's see, 0x64, no padding required, is simply APB2 low power enable. Copy this. Right, and the one after that, let's take a look at it. So the address is 0x64. The next one has to be 0x68, otherwise we would have to pad. Okay, we have to pad with 2 32-bit data types in order to arrive at this position. So I'm going to call dummy number 8. I'll just copy our dummy and then change it to dummy 8. Right, and once that is done, we can call our register __ IO. I'm enjoying this. I hope you are. Very exciting. You and I will construct the library from scratch, and you see how easy it is. Yeah, so the name of the register is this over here, BDCR. Yeah, I wasn't always like this. When I started embedded programming, I think this is the year 2019, 2020. Actually, today is 2020. If you're watching the video, I'm recording this video on the 2nd of January 2020. So when I started embedded programming, I think that was about let's see, 2012. That's been, goodness, like 8 years ago. I didn't like the data sheets that much and the reference manual, but I developed patience, and I realized in order to be able to really use the device the way I want to use it, I have to understand the reference manual and the data sheet. And if I want to take the practice seriously and become a professional, then I have to start reading such documents. So ever since I came to that realization, whenever I buy a new device, I spend time getting acquainted with it, reference manual and data sheet, and constructing the libraries from scratch. I did that when I was a student, but now I'm a professional. I own a business, and I'm the engineer in the business, and it's been very helpful. So I hope you find it helpful to understand these type of things. Okay, so yeah, this is where we left off before I started ranting. So this is the address. The next one, let's see, it has to be 0x74, otherwise we would have to pad. Okay, no padding required. Is the clock control status register. I'll just copy this. __IO UN32_T. That's the name of the register. Okay, let's see. So the next one should be 0x78, otherwise padding will be required. But from what we've learned from the past, it's as if we pad after every 0xx4. Whenever it ends with 4, we apply padding. So I suspect we may need to pad, but let's see. Of course we need to pad because we are at 0x80. We need to pad with 2 uint32 data types. I'm gonna use the array method over here to give us 2 of them. This is dummy number 9. Right, once that is done, we can create spread spectrum control generation register. Copy this, and then __IO UN32_T with this like this. Okay, let's see who is next. Okay, no padding required. This register is called the PLLI2S configuration register. Simply copy this, and then come over here, __IO UN32_T like this. Okay, who's the next one? So the address currently is 0x84. The next address has to be 0x88. If it's greater than this, we would need to pad. So I'll go the next one, it's over here. So we need to pad with a single uint32 data type. So I'll come over here and I'll say uint32_T, and I'll call this dummy 10. We need a single one this time. Once that is done, we can get a register, dedicated clock configuration register. That's the name of the register. Copy this, and then __IO UN32_T like this. Okay, we are done. Let's see, are we done? Right, we are done. Okay, so we are done with the RCC registers. That's good. It's really good. Let's see what we have. Right, so we have the structures for our GPIO as well as RCC. So the video is getting quite long, so I think we should end this particular lesson here and continue in the next lesson. In the next lesson, we're going to test our GPIO driver. Right, I'll see you.